So we're moving on to predicting equilibrium concentrations. Hey, buddy, it'd be really nice if you mix a couple things, and you know how much you mixed, and you know it's all going to react. It'd be so much easier, but it never all does. So now you've got these calculations involved. How much is going to be left? How much is going to be produced? And if you just wait around long enough, you can get the right answers, but you got to be able to calculate this stuff. And yeah, it's changing over time, but sooner or later you get these constant concentrations with reactions, and that's kind of what we're talking about. It's just what concentration of reactants and products are you going to end up with if you wait around long enough. You're at equilibrium. Okay, so that has to do with pretty much everything. I mean, the prescription drugs that people are taking, photosynthesis, commercial products. Right? Everything's at a chemical equilibrium if you wait around long enough. Okay, so we did this demonstration already. This, and I jumped ahead. I wasn't supposed to. But see if you remember it. Remember when we were talking? We had these. I think Kendall and I don't know. Somebody was up here, right? And Megan, and you guys were doing the beaker war, right? You had someone had a small beaker, one other person had a large beaker, and they just like this. Okay. So what does chemical equilibrium being dynamic refer to regarding this imaginary demonstration that you already saw? What did it mean, Bowdy?
At some point, they just think it doesn't matter that one of the beakers is bigger, it's going to be the same.
Yeah. At some point, you're transferring the same amount from reactant to product and product to reactant. It didn't matter how big the beaker is. It didn't matter how large the rate constant was for that forward or reverse reaction. You're going to be transferring the same amounts from reactant to product and product to reactant. You can't stop it. It's always happening. So that's why it's dynamic, even though the concentrations aren't changing over time. So when is equilibrium reached? I think that's the answer. When the concentration of any reactant or any product is not changing over time. It's constant. Even though the equilibrium is dynamic. You've got reactant being converted to product, product being converted to reactant. The point is their concentrations aren't changing over time. So if you take all of these concentrations then, right? If you take all these concentrations and divide them by one another, you're always going to get a constant number. Now they want the concentrations of what on top in these equilibrium constant expressions? Which one is it? Kendall, which one is it? The concentrations of the what on top? Right? Because we have these reactants going to products. Well, it's supposed to be dynamic. You should draw double arrows, right? And if you wait around long enough, the concentrations of all these products and reactants, they're not changing over time. So we're just going to divide the two, and we're going to get a number. But you always got to divide what by what? What has to be on top? The products. The products got to be on top. And the reactants got to be on the bottom. So make sure you draw those brackets, because that's important. These brackets, those brackets mean what? Concentration. And we're going to use what units? We had a lot of choices for concentration. Connor, which one do you think they're going to use every single time? Molarity, big M. They're going to use big M every single time. And you wouldn't have to use concentration. You could use, if it's a gas, you could use pressure and things. But they say no. C, we want concentration for everything. We don't care whether it's what phase it's in. We always want concentration. Okay. There's going to be some things that are never included in any equilibrium constant expression. So equilibrium constant expression, again, that's Kc equals, all these products over all these reactants, right? You just plug them in. Except if that product or a reactant is a what, you're not supposed to include it. Solid. Don't include it. It's not written. You just ignore it. Solids, there's another one. Oh, not gas. Only one left, liquid. Solids and liquids. They don't want you to include. Come on in, Cam. They don't want you to include in KC expressions. Okay. Why? Is because their concentration is a constant. You're just going to bring it in over here. And for example, water is 55.4 molar. So don't, just whenever you see solids and liquids, do not include them in the equilibrium constant expressions. So we're going to be going to the boards and doing a bunch of this stuff, but not yet. We just want to talk about this and one other topic. Let's see if we can practice it, though. Write the equilibrium constant expression for each reaction. So Audrey, you've got this first one. Kc is supposed to be something over something. What would you put on top? Audrey, what would you put on top? The CaCl2. And you got to put it in brackets. Then on the bottom you'd put Ca with a +2 charge. Okay, now here's the question. Is it plus or minus here? Or she's going to write the Cl minus. What goes right here? Multiplication. It's multiplication. It's always products over reactants, and everything's multiplied. But how many Cl minuses do I have? 2 of them. But you're never going to do this. Right, Enrique? That's too much writing. You're always going to do what? Put an exponent. Right? Those stoichiometric coefficients always become exponents. Because we're too lazy to write the same thing out 2-3 times. We could. There'd be nothing wrong with it. Okay. How about B? Write out B, and then we'll see if you guys agree on it. Heck, do them all, then we'll ask you. Ask somebody. Andromeda, before we answer B, just make sure you realize, everyone realizes, I and everybody else are too lazy to write what subscripts down here. We're supposed to be writing them. Andromeda, what am I supposed to be writing? AQ. Means that it's dissolved in water. So we're always too lazy to write it, right? Okay. So how would you write, Jose, the answer to the first one? What over what? Yeah, B. 1 on top, perfect. Perfect. How about C? Anessa.
Concentration of O2 on top over concentration of carbon dioxide.
Perfect. And the last one, D. Andrea. And then exponent where? Yeah. Looks right. Everybody agree? Perfect. Okay. So that's part of the homework, writing equilibrium constant expressions. Just leave out what and what, everybody? Solids and liquids, and then you'll be fine. Okay. Using ice tables to predict reactant and product amounts at equilibrium. Okay, an ice table. Kenneth, what can you imagine ice is going to stand for? An ice table is going to look like this. We're going to have a reaction, and then we're going to write I, C, E. That's an ice table. Yeah, all these reactants go into products. And underneath, we're going to make a little table, I, C, E. What do you think I, C, and E stand for?
Does the C stand for concentration?
We're going to be plugging in concentrations. C stands for change. Anybody? I is for initial, and E is for equilibrium. So initial, change, equilibrium. We have to write those 3 rows, and it just organizes things so much better. Okay, because these problems get really wordy. Look at this. 8 moles of A and 6 moles of B are initially present in the below reaction. 6 moles of C are found at equilibrium. How many moles of A and B are also present at equilibrium? So this isn't concentration, this is moles. So you could either make a mole ice table, or you could make a concentration ice table. They're both perfectly legit. Just what's not legit is a grams ice table, because reactions involve numbers. This number of molecules react with this number of molecules to make this number of molecules. So you got to be talking about moles or concentration. All right. We want to know how many moles of A and B are also present at equilibrium. So you make an ice table. Mia, all of these answers at equilibrium are in which row again? Which row are you supposed to be looking at for your answers at equilibrium? The what row? There's an E. Well, it is an E, right? The E row. The E row has all of your answers at equilibrium. So let's see if we can start filling it in here. Whoop, no name. Your English is better. Your printing is better than mine, though. Bowdy. Let's start throwing some stuff in this ice table. What would you put in here? 6 moles of C are found at equilibrium. Where are you gonna put that? Definitely put that in the E row and put it under the C. Okay, now here's a question. Megan, we've got a stoichiometric coefficient of 3 in front of that C. Should we write 18 instead of 6? Oh, should we write 6 to the 3rd? I don't know. I'm just trying to be devil's advocate here. Remember, the E row is the answers. How many moles of C are at equilibrium? 6. So you better write 6. This is a common mistake. I don't know why people do it. Right? It's 6. So write 6. Okay. Those stoichiometric coefficients don't matter, at least in this row. Okay, some more stuff to fill in here. Kendall.
Put the 8 moles
Under the
A.
A. In which row? I. Good. Now again, do you put 8 or do you put 16? Or do you put 8 squared? You put, everybody? 8, because that's the initial. That's the initial A. Keep going. Another one. Connor. 6 under the B. Okay, there's more stuff we can fill in here, Audrey. What can we put under the, what can we put right here? Was there any C there initially? No, so you would put what number? 0, or a dash. Zeros and dashes, same thing, right? Or dash. The change row, Steph. Now, when we're solving problems, we can use a lot of different variables, but whenever you're solving for something, people usually pick what variable? X. X is just what people like to use, so we're going to use X too. What's the change under A? First, is it going to be positive or a negative change? Right? Are we going to get more A when you reach equilibrium, or are we going to lose A? We're going to lose A. Yeah, definitely, because look, all we have is reactants. These are definitely going to be negative changes for both of these. But negative what? Well, we got to figure it out. So for negative, Enrique, how about under A? Negative, we could write X, because that's supposed to be our change. But negative X for B2, let's get you going here. But are those changes the same? Do you have the same amount of A as you do B disappearing? No. In fact, whose change is bigger? A's bigger. By what factor? 2. So this has to be negative 2x. Has to be negative 2x. And then to get the equilibrium, well, just add the initial and the change, right? Because this, how much did it change by? Well, 8 minus 2x. 8 plus a negative 2x. Right? B, 6 minus x. Oh, we forgot to write in a change here. How about for C? Is it 3x, positive 3x or negative 3x?
Positive, it's a product.
Positive 3x. It's being formed. You can put a plus sign in there. Okay. Our ice table is done. Our ice table is done. What we did is we got all the initial numbers just from the reading, the change, negative for reactants, positive for products. And how did we get these numbers again out in front of the x? They're always the what coefficients? They're always the stoichiometric coefficients, every single time. Then how did we get the E row? We just what? Added them up. Okay. Our answers are supposed to be here. There's just a trick to figure it out. You got to figure out what x is. Alyssa, how are you going to figure out what x is? Right? These are supposed to be our answers. I guess the trick is right here. 6 and a negative x is 6 minus x. So A's answer is 8 minus 2x. B's answer is 6 minus x. C's answer is supposed to be 6. But 6 is also... 6 is going to equal what plus what? Right? Because how do we get this E row? If we didn't have that 6, you would have wrote what down there? 3x. Because 3x plus 0. But 3x, everybody's equal to what? 6. That has to equal 6. So 6 has to equal 3x. X has to be 2. Now you can write down all the answers. Right? At equilibrium, moles of A, moles of B, and moles of C. And draw a box around your answer. Right? So Andromeda at equilibrium, the moles of A is going to be what number? Right? If x is 2, then here's your answers. They're supposed to be all in this E row. A would have to be 8 minus 2 times 2. Just get 4, right? 8 minus 2 times 2. B, everybody? 4. C, 6. and you're done. Okay? All right, so now let's just finish the hour. We've got like 20 minutes or so or more, and just see how many of these we can get through. Okay, we've got plenty of board space. You can help each other out. And by the end of the hour, I think you're going to be pretty comfortable with this stuff. Let's give it a shot. Join us, Jose. We're going to go to the boards. I got all brand new pieces of chalk up at the boards. Everyone's got a nice big hunk of chalk. No way. Didn't even bank it.
Yeah, food on the line today. That was for lunch. That's for lunch. And I ate it today.
Oh man, I would have bet him $1. I was gonna make $1. So spread out as much as you can. There's a lot of space. What is the equilibrium composition for the below reaction if initially present were 4 moles of calcium, 6 moles of phosphate, and equilibrium you got a half mole of calcium phosphate? Ice table. All these equilibrium problems are ice tables. Whenever they're asking for what is the concentration at equilibrium, man, it's an ice table every single time. Oh, there's plenty of space. Over there's a whole board all to yourself.
Oh, separate. Oh, okay, that was together.
Separate. You just be watching those guys. You wouldn't do anything. Remember, to get this one, you just add them up and get that one. Oh, because the change has to, this 4 has to go down. That's going to decrease. That 6 is going to decrease. And this is going to increase. So these are always going to be positive changes. And these are always going to be negatives.
Okay.
And they're all going to be x's. But just how much? 3x, 2x, and 1x. You always go by the little number up front.
Okay, that's okay. I got you. Steph, how'd you get that? A 0.5.
Yeah.
Right?
Yeah.
And then this is where I get lost right here.
So for here, these are always, this 4 is going to decrease. That's going to decrease. Well, you need a number here. That's 0, right?
Oh,
That's
yeah.
there initially. This is going to increase. So the change row is always x's.
Okay.
So this is going to be positive x's, negative x's, and negative x's because they're reacting. And then what you got to realize
Always,
is
so these are always going to be negative. Is there ever
the changes are always going to be negative for
Yeah.
reactants.
Okay.
And then just how much negative x? Well, 3, 2, and 1.
Wow. That's it. And then you solve for it?
So when they don't have them, like, so on this,
Well, if there's nothing there, we're too lazy to write ones.
So then
Just like here, Audrey didn't write 1. No one writes ones.
like for this one, how we did it, you don't go by like this difference, like 8
So now,
and
you
6.
have to add them up to get the answer in the equilibrium row. 4 and a negative 3x, 6 and a negative 2x, 0 and x.
You know what I mean? So why on this one did we do the difference between the 8 and 6? Like that's a 2.
Oh, we didn't. We didn't. That 2 came from this.
Oh, okay. Okay.
Yeah.
Once you get the whole table filled
Okay,
out,
and now your x here, this has to be x has to be 0.5.
oh, so it just comes down.
Yeah, because 0 plus x, because if you didn't want to write that in, it might be better. 0, that has to be x. And then, but they told you that this answer is really 0.5. So if x is 0.5, you put in 0.5 for x, and you get all of these.
Oh,
So I think it's probably sometimes easier to see if you don't put in the answers at equilibrium, because then it's easier to see, oh yeah, he's got x is going to be 0.5. So, but it's up to you, however you'd like to do it. And keep going. If you get the same answer as the folks around you, just keep going.
This one, they just want the expression. You don't have to actually do that.
They just want
They just want the expression. So they
calculate
do
a
all
value for Casey. You need a number.
they keep getting 3.5.
Yeah. They want 3 times 0.5 is 1.5. So
Oh.
1 point, right? What's 3 times 0.5? 1.5. So if you do it on the calculator, just 2.5.
Oh, that
Right.
is like.
If you take
this
4
in parentheses.
4 minus, well, you could do parentheses, 3 times 0.5, but
Oh.
you don't need parentheses. I mean, even if you did them, you'd be fine. 4 minus 3 times parentheses 0.5, close parentheses, same thing.
Oh. Okay.
Yep.
So you said that these would all be negative since they decreased, right?
Yep.
Okay, well, how come if these are, would that be positive?
Well, no, the change row is always negative. Here you just write in initial amounts.
Okay.
Change row is always negative for reactants, positive for products. And it always involves x, the x's. So negative x's for reactants, positive x's for products. There you go.
Thank you.
Yep.
Concentration's always moles over liters, right?
Moles per liter. Remember, negative for reactants, positive for products. Yep. You guys giving up on the boards already?
No, no.
No, I'm writing my answer down.
I'm right,
Oh.
yeah.
So when I try to do this later, I know.
Yeah,
Oh.
exactly.
You don't. If you get through all of these problems on the board, you're going to be confident if you do the homework. That's the idea.
The homework's always a lot harder than the class.
So true.
I'm like so
Well,
confident in class and I go.
That's
home and
why.
try to
That's
do
why
it
you got to
myself.
get going. In other words, because your hard problems are down here. So I want to build in and get comfortable with it, and then there's going to be harder questions in here. So that's why I want to see if you can get to it.
For this one, we're writing that Kc equals the
Right, the expression. Yes, Kc expression is concentrations of products over concentrations of reactants. raised to their stoichiometric powers. Yep. Yep.
So do I just leave it in mold right here and just plug it in? Or do I convert that to molarity?
Oh, yeah. That's good. See, you wrote this. So I would find the concentration of that one and divide it by these two concentrations. And you're right. It's always moles over liters.
So I have to find the molarity of each one?
You have to find the molarity of each one and then plug it in. Yep. So yeah, let me write down your answers. You got 1.23. 2.345. 0.25. Anybody else get those? So keep going. See if you can get to the harder ones. Yes, except you have to have moles, because these are brackets. That means moles over liters. So you have to find the concentration of each one of those, divide the moles by the liters, and find each of those, and then divide them. You see that? So if you're working on 44, I see a lot of folks working on it, and their very first step was to write that Kc expression. They're really on the right track. Yeah. Right? And then you got to realize concentration is moles over liters. So you got to find that concentration for every single compound in your Kc expression. And then you divide it and find it.
Right here, when it says a sample of this one, does it count as the I or the E? Because it didn't say initially here.
It doesn't. But it says you have this, then you have this, gives an equilibrium mixture of this. So here's your E for that NOBR. But if it gives it, that means this had to be your initial.
Okay.
Did anybody get an answer for 44? Yeah. What did you get? 39.14. 39.14? Anybody else get 39? Enrique got 39? So if you're getting 39 for 44, you're on the right track. Good job. Keep going. Oh, did you see? Want to see that? right? Just divide moles by liters every single time.
Is the composition the same
As a constant?
what is the composition?
Yeah, they want to know what are the answers at equilibrium for everything. That describes the composition.
Once you get
What's the equilibrium
concentration for each of them, you put them into this?
Yes, and then you substitute them in.
So you would multiply these two first and then divide?
Well, I would just take this, divide it by that, and you're done.
Oh, okay. Oh, that sounds good.
All right?
All right.
Do it in one big step. Yep. That's a really good question. Equilibrium constants don't have units, and it looks like it should, right? Because then all the units don't cancel, but they don't and that's an advanced chemistry question. You have to get into activities. So we're really not telling the whole story here, but we'll wait on that.
Do you just want us to try?
So we don't put units. Just put a number. Mm-hmm.
What do you mean by composition of equilibrium?
They just want to know what are the answers for everything at equilibrium. So if you know what the amount of each one of these at equilibrium, then you know its composition, what makes it up.
So we did like ice again?
Yeah, just do ice again. This is a fancy way of asking for what are all the answers at equilibrium again. What are the amounts? In 55, how did you guys handle this 1/2? Make it an exponent. Can you have fraction exponent? Yeah. In fact, half means square root, right? Now, if you don't like halves, you could multiply everything through by 2 and write the Kc expression for that. But you're kind of changing the reaction. But because you're going to have a different Kc for different reactions depending how it's written. But well, you can, but then you better be really clear. You better put the numbers on here, and then that's the Kc expression for that reaction. Because the exponents are going to be different.
What are your point on that? What is it when it's a 5? And we're going to stuck it this part.
Okay. So does the pressure and the temperature mean anything? Nah, you don't really care, right? So you're going to do this ice table, and you have the initial, right? And then you have, here's your equilibrium for PCl3. It's going to work.
Yeah, but like
You just-
it doesn't give one for chlorine. Oh wait,
Yeah,
chlorine.
well, that's 0. It'll be 0 too.
Okay. Okay.
All right? Just keep going.
I did ice again.
If you get down to 29, notice how you can completely disregard this stuff. It doesn't mean anything. Temperature and pressure, that doesn't even fit into the Kc expressions. You don't care. So it's just there to confuse you. Okay. But
We're confused as to how to set up.
Okay. Is it asking for amounts at equilibrium again?
Ask for the composition.
Yeah, that's a fancy word for amount.
Okay.
What are all the different amounts at equilibrium? Because if you know all the amounts at equilibrium, you know its composition. It's just a fancy way of saying it. So that means it's definitely an ice problem.
Okay.
Whenever you're after something, the amount at equilibrium, it's always ice.
Because you can have a mole ice table.
You can have a mole or a concentration ice table.
What are we going to do with mole? There's no liters. How's the
Yeah,
concentration?
yeah. So it's
But you can use the mole.
well, yeah. Your moles are gonna be your answers.
Okay.
That will be the composition. You tell the moles at each compound at equilibrium, and that'll be the composition.
So every time it says equilibrium is when we do ice and then when this
Yeah,
one
that's
doesn't?
what. Well, no, because.
Well, whenever you want to know the amount of something at equilibrium, it's going to be ice. So here they want to know what is it, final reaction mixture. Well, that means equilibrium, ice problem. What is the composition? What are the different amounts at equilibrium? Ice problem. It's just different ways of asking for the same thing, and then the English always makes it harder.
So when it doesn't give
Oh,
me
keep
the-
going. How much? You have 0 for this. You're going to have also a
Zero.
0. Now, you'd leave it out, Enrique, and not write anything if that was an S or an L. But it's a G, so you have to keep going.
Yeah.
So you need to
So
write.
we need to find the.
You need to write an X over here
the
too.
equilibrium of these two.
Yeah.
because
So
it's the reaction
because you have to finish the table here. What would you put on right there?
Plus X.
Plus X, and then final answer is just going to be no for this guy.
Oh,
X plus 0 X again. Yep. And you got it.
What would you call these? There's still mole B and mole C? Mole, like in here.
Yeah, you're making the mole table.
Mole A, B, C? Like in the answer?
Yeah, yeah. That'd be the easiest way to do it. I don't do A, B, C though, because how do you know what's A, B, and C? I would say moles of PCl5.
Okay.
Moles of. Otherwise, I don't know what A, B, and C would be. What's that?
Oh, I was asking, is that the last equation?
For the very bottom one?
Yeah, the bottom one's at the last one.
Yep.
I was trying to
We're going to get the exams back in a couple minutes here. Oh, okay. So we have about 5 minutes left. See if you can wrap up the problem you're on, then we'll hand back the exams.
I saw my grade. That's horrible. I don't know what happened.
Well, yeah, come in and ask questions.
Next time, guaranteed.
I don't think I put my name on that.
That one's yours? Color coded?